Hello dear students, this is Professor Anindya Das from Achievers and welcome to my lecture series on the second law of thermodynamics. In today's lecture, we will be dealing with a very important experiment in context to the second law of thermodynamics. It was rather a revolutionary leap in context to the second law of thermodynamics, and that is our Joule-Thomson expansion. It is very important in context to the second law of thermodynamics. It has multiple uses, so we will understand it in due course in context to this particular lecture. Okay, so let's proceed into the lecture where we will study the fundamentals of this Joule-Thomson expansion. So at first, let us construct the experimental setup of this Joule-Thomson process. So what we have an adiabatic enclosure. Okay, we have an adiabatic enclosure like this. We have an adiabatic enclosure like this. Okay, and what else do we have? We have got a setup like this. I've got a setup like this. I'll explain it. See, this is basically a porous plug. This is basically a porous plug which is only permeable to gases. This is basically a porous plug. This is a porous plug which is permeable to the gases. This is a porous plug which is permeable to the gases. Fine. And you have got a piston both in the left hand part and the right hand part of the porous plug. So what we have? See, this is a frictionless piston. It is on the left hand part of the porous plug, and this is another frictionless piston which is on the right hand part of the porous plug. Now you can see there is a gap between the left hand piston and the porous plug. Okay, and the gap within the left hand piston and the porous plug is filled with gas molecules. Let the pressure be Pi, volume be Vi, and temperature be Ti. Okay. So this is the left hand part and this is the right hand part. And what do you find it's happening in the right hand part? In the right hand part you see the piston is stuck with the porous plug. And as the piston is stuck with the porous plug, so there is no gap between the piston and the porous plug. And as there is no gap between the piston and the porous plug, so in the right hand side you don't have any gas molecules. So in the right hand side the piston is in contact with the porous plug. Okay, fine, understood. Now In case of this Joule-Thomson expansion, an essential condition has to be maintained. An essential condition has to be maintained. Or rather, essential conditions. There are two essential conditions. The first one is, as I have told, this is an adiabatic enclosure. This adiabatic enclosure denies any heat flow through these walls. It denies any heat flow through these walls. Okay? And so this is the first condition. Adiabatic enclosure. And what is the second condition? The second condition is the left hand pressure should always be greater than the right hand pressure, or the left hand initial pressure Pi is always greater than the right hand pressure. The left hand initial pressure is always greater than the right hand pressure. So dP is negative. The left hand initial pressure is always greater than the right hand initial pressure. Right hand pressure, in the right hand side, you will maintain a pressure of Pf. This is constant. In the left hand side, you will maintain a pressure of Pi, which is also constant. And Pf should always be lower than Pi. That makes dP negative. So in the right hand side, you are artificially maintaining a constant pressure of Pf. That is regarded as the final pressure. And in the left hand side, you are constantly maintaining a pressure of Pi. That is regarded as the initial pressure. And the essential condition is Pi should essentially be greater than Pf. That makes dP negative. So this is the fundamental criteria of a Joule-Thomson process, where the change in pressure dP is said to be negative. Understood? Now, if you are maintaining a constant high pressure over here in the left hand side and a constant low pressure in the right hand side, then what is going to happen? Then obviously the gas molecules will flow from the region of higher pressure to the region of lower pressure through the porous plug. The porous plug is permeable to the gases, so there is no prohibition for the gas molecules to pass through the porous plug. The gas molecules will pass through the porous plug from the left hand direction, that is in the region that is corresponding to the region of higher pressure, to the right hand direction, which corresponds to the region of lower pressure. So there will be gas flow, in this direction. There will be gas flow in this direction. The gas will flow from the region of higher pressure to the region of lower pressure. That is the natural tendency. The gas molecules will flow from the region of higher pressure to the region of lower pressure. That is going to happen. So in the final stage, you'll see what has this transformed into. It is transformed into the situation like this. Now the left hand piston is going to get stuck to the porous plug. On the contrary, the left hand piston is going to get stuck to the porous plug because all the gas molecules has flown out of the left hand compartment, and that's why what is going to happen, this left hand piston is now going to get stuck to the porous plug. It comes in contact to the porous plug, and thereby the situation arises where the left hand compartment gets completely evacuated, as all the gas molecules has flown from the region of higher pressure, that is from the left hand side, to the region of lower pressure, that is the right hand side. Okay. So after this process has got executed, what the picture will look like? Now the left hand piston comes in contact with the porous plug, and the right hand piston will now move away from the porous plug, because now the gas is going to get accumulated in the right hand compartment. The gas has flown from the left hand compartment entirely to the right hand compartment. So so now the gas molecules will get entrapped in the right hand compartment. Okay, and thereby the right hand piston will move away from the porous plug, and you'll see the gas molecules over here. And this is said to be the final situation, where we have already mentioned that the pressure is going to be Pf, and let the final volume be Vf and the final temperature be Tf. And all we know is that Pf ought to be lower than Pi. That's known to us. So these are the two essential criteria. Okay. Now, keeping this experiment in mind, we will try to make some important mathematical interpretations. So this was our experimental setup. So I've understood the experimental setup. Now students, let's move on to the mathematical interpretation. Mathematical interpretation. Okay. So what conditions do you have? You have adiabatic enclosure, that makes Q to be equal to 0, and you have Pf less than Pi, that makes dP less than 0. So these are the essential conditions. Okay. Now you have to calculate the work done. The work done is equal to W left plus W right. So what is happening in the left hand side? Let's check. In the left hand side, the pressure is Pi, and the volume changes from Vi, it was initially equal to Vi, and finally the left hand piston gets stuck to the porous plug, so the final volume in the left hand side becomes 0. Initially the volume in the left hand side was Vi, and as all the gas molecules flows out of the left hand compartment and moves into the right hand compartment, thereby the volume in the left hand side is reduced to 0, and the left hand piston comes in contact with the porous plug. So in the left hand side, the pressure is Pi, so minus Pi, the final volume is 0 and the initial volume is Vi. Done. we are already acquainted with the formula of work, minus P delta V. So minus P is Pi and delta V is V final minus V initial. V final for the left hand side is 0 and V initial is Vi. Now let's move on to the right hand side. What is happening in the right hand side? You see, in the right hand side the initial volume was 0. Initially in the right hand side, what do you find? We find that the piston is in contact with the porous plug. So the initial volume in the right hand side was 0. And finally, as all the gas molecules flows into the right hand compartment, the volume becomes Vf. So the final volume is Vf and the initial volume is 0. And what is the pressure? The pressure is maintained at a constant value of Pf. So you see it becomes minus Pf whole multiplied by final volume Vf minus initial volume 0. Understood? And thereby W becomes Pi Vi minus Pf Vf. Now by first law of thermodynamics, what we have? We have delta U equal to Q plus W. Now what is the value of delta U? Delta U is U final minus U initial. Q is equal to 0. We already know that. And what is the value of W? W is Pi Vi minus Pf Vf. So if you rearrange both the sides, then you'll see Uf plus Pf Vf becomes equal to Ui plus Pi Vi. That makes Hf to be equal to Hi. Because according to the definition of enthalpy, we know that it is equal to U plus Pv. So you find Uf plus Pf Vf equal to Ui plus Pi Vi. That makes Hf equal to Hi. That means dH is equal to 0. So one more essential condition has been added to it. One more essential condition has been added to it, that is dH is equal to 0. Okay. Now you have to identify whether this process is reversible or irreversible in nature. Then we can make some important conclusions. At this juncture, we need to know whether this Joule-Thomson expansion is reversible or irreversible in nature. For that purpose, we need to make some important interpretations. So, checking the reversibility or irreversibility of Joule-Thomson process. We need to check this. We need to check this out. We need to check this out. Now we are acquainted with the fact that H is equal to U plus PV. That makes dH equal to du plus PdV plus VdP. Again, d cut q reversible is equal to TdS. We are already acquainted with this fact, which is equal to du plus PdV. This is for reversible process with no non-mechanical work. We know this thing. For reversible process with no non-mechanical work, what is going to happen? TdS should be equal to du plus pdv. We are already acquainted with this fundamentals of the second law of thermodynamics. Now, we will replace this du by TdS minus pdv, which is coming out of this equation. See, we can replace this du by TdS minus pdv, because from this equation we find that du is equal to TdS minus pdv. Now if we do so, what do we get? We get dH to be equal to TdS minus pdv. Basically we are combining these two and we are getting dH equal to TdS minus pdv plus pdv plus vdv. Now these two pdv terms will get cancelled out. And also we know that for Joule-Thomson process, this dH is equal to 0. We have already proved that for Joule-Thomson process, this dH is equal to 0. So on substituting, we are getting TdS equal to minus VdP. TdS equal to minus VdP. So that makes ds to be equal to minus V by T dP. So that value of ds becomes minus V by T dP. Minus V by T dP. Now you see, this is ds system. ds system is minus V by T dP. Now students, we already know that the sign of dP is negative. dP is negative. We already know that dP is negative. So this dP is negative. V by T is always positive. V is a positive term, capital T is a positive term, so V by T is always positive. So you see, negative into positive, negative multiplied by negative, it's positive. So ds system becomes positive. And what about ds surrounding? ds surrounding is equal to 0. Why? Because you have maintained an adiabatic enclosure, and due to this adiabatic enclosure there is no heat interaction between the system and the surrounding, thereby ds surrounding is equal to 0. We already know this thing. If we maintain an adiabatic enclosure, then ds surrounding is going to be equal to 0 due to the lack of any heat interaction between the system and the surrounding. So this is due to the adiabatic enclosure. Therefore ds universe, positive plus 0 is positive. ds universe is ds system plus ds surrounding. ds surrounding is 0, ds system is positive. So naturally ds universe is positive. And if ds universe is positive, then according to Clausius inequality, the process is ought to be irreversible in nature. So we find that Joule-Thomson process is irreversible in nature. So till now we find that for Joule-Thomson effect, Q is equal to 0 due to adiabatic enclosure. dP is negative. dH is equal to 0 and the process is irreversible in nature. Okay. Now, these two conditions will lead to a very important conclusion. Apparently, we see that dH is equal to 0. If dH is equal to 0, then the process apparently seems to be an isoenthalpic process. The process seems to be an isoenthalpic process. But Joule-Thomson effect is not an isoenthalpic process. So there is a fallacy. There is a fallacy. Apparently, as dH is 0, the process seems to be an isoenthalpic process, but in actuality, JT effect is a non-isoenthalpic process. It's not an isoenthalpic process. Now I have to explain this. Although JT effect apparently seems to be isoenthalpic in nature, it is actually a non-isoenthalpic process. You have to explain this. This is a very important question. You have to explain this. You have to explain this. This is a very important conceptual question. You got to provide a suitable explanation for this. You see, for reversible process, what happens? For reversible process, you have infinite number of steps. So, between the initial and the final states, you have got infinite number of steps. Infinite number of steps connecting the initial and the final states. You have got infinite number of steps connecting the initial and the final states. And if there are infinite number of steps, then there are infinite number of states between I and F. Between I and F. So for a reversible process, you have infinite steps between I and F. That is, it results in infinite states between I and F. Okay. Now, had the process been reversible, if Joule-Thomson process had been a reversible process, let us consider it to be reversible, then for all this infinite number of states, H will be held constant. If Joule-Thomson process was reversible in nature, then between the initial and the final states, you will get infinite number of steps, infinite number of states, and thereby H will be held constant for all those infinite states. So, if Joule-Thomson process was reversible, then H would had been constant for all the infinite intermediate states. If this condition is held true, if this condition is held true, then a process will become truly isothalpic. If H is maintained to be constant throughout the process, then only it is truly isothalpic. So, if this was true, if this was true, then H would had been constant throughout the process. And thereby you can say that the process is truly isothalpic. And thereby the process becomes truly isothalpic. But this is not the actual situation. But this is not the actual situation. Actually, the process is irreversible in nature. And as the process is irreversible in nature, then you cannot figure out this infinite number of steps or infinite number of states in between I and F. And thereby you cannot say that H has been maintained constant in all those infinite number of states. Then you cannot say that H has been maintained to be constant throughout the process. So, in that sense, although the initial and final enthalpies are same, the enthalpy in between I and F cannot be predicted, and thereby the process is not truly isothalpic. So, for irreversible process, H is not constant throughout the process. As it is irreversible in nature, H is not constant throughout the process. And as H is not constant throughout the process, so you can say it is truly not isothalpic. It is truly not isothalpic. So this is very important. This is a very important conclusion. This is the conclusion. This is a very important conclusion. This is a very important conclusion. This is a very important conclusion. It is not truly an isothalpic process. And now we know this thing. So, we have made an effective mathematical interpretation of this Joule-Thomson process, and we have found out some important conditions or results arising out of this Joule-Thomson process. Okay. Now, we will introduce a very important term in context to Joule-Thomson process, that is mu Jt, which is Joule-Thomson coefficient. Okay. So we will understand the meaning of mu Jt in this context. Now, according to the fundamental definition of this Joule-Thomson coefficient, we can say that mu Jt is equal to del T del P at constant H. This is the fundamental mathematical definition of the Joule-Thomson coefficient. It is basically the rate of change of Kelvin temperature with respect to pressure at constant enthalpy. Okay. So this is the fundamental definition of Joule-Thomson coefficient. Let us mark this as equation number 1. So this is the fundamental definition. This is the fundamental definition of Joule-Thomson coefficient. And from the mathematical form, we can say that it is the rate of change of Kelvin temperature with respect to pressure at constant enthalpy. Now, we will derive some important equations pertaining to this particular parameter, that is Joule-Thomson coefficient. But before that, we need to know the significance of this term. So now we'll know the significance. You see, dP is always negative. This is the fundamental condition. This is the fundamental condition pertaining to Joule-Thomson effect. So dP is always negative. Now, we know that this particular parameter is negative. Now, if this mu Jt is positive, then what is going to happen? If mu Jt is positive, if this becomes positive, then something by negative is positive. That means dt has to be negative, because negative by negative is going to be positive. So under this situation, dt becomes negative. If dt becomes negative, then that means there is a cooling effect, because the change in temperature is negative. That makes the final temperature to be lower than that of the initial temperature, and thereby it is ought to have a cooling effect. So this leads to cooling effect. CE means cooling effect. Now, if mu Jt is 0, then what is going to happen? Something by negative is 0. That means that something is 0. If mu Jt has to be 0, then dt, del T has to be 0, or dt has to be 0. 0 by negative is 0. So if mu Jt is 0, then this dt has to be equal to 0. This is quite understandable from this particular equation. So if mu Jt is 0, then dt is equal to 0. That means there is no effect. N stands for no effect. The process becomes isothermal. There is no change in temperature. The process becomes isothermal. Now, What if mu jet is negative? If you want to make mu jet in negative, dp is already negative. So if you want to make mu jet in negative, then dt must be positive, because positive by negative is negative. So if mu jet is negative, then dt must be positive. That means there must be heating effect. So if mu jet is positive, if mu jet is negative, dt is positive, that leads to He or heating effect. So for a particular process, if we find mu jet is positive, then there must be cooling effect. If we find mu jet to be equal to 0, then there must be no effect, the process is isothermal in nature. And if we find mu jet to be negative, then there must be a positive change in temperature that leads to heating effect. So this is the significance of this particular parameter, Joule-Thomson coefficient, which is denoted as mu jet. Okay. So from the sign of mu jet, we can understand the nature of the process, whether it would lead to heating effect, cooling effect, or no effect. That is understandable from the sign of mu jet. And that is established from the fundamental definition of this particular parameter mu jet. Okay. So these 2 points are the rudimentary interpretations of this particular parameter, Joule-Thomson coefficient. Now we'll move on to some important mathematical treatment of mu jet, and we will derive some important mathematical relations in context to this particular parameter mu jet. So let's proceed. You see, in this particular case, as per the fundamental definition, we know that mu jet is equal to del T del P at constant enthalpy. Now, in this context, we'll be using the chain rule of state function. And as per the chain rule, what we can do, we can split this term into 2 terms like this. Del T del P, del H. So it becomes del T del H at constant P and del H del P at constant T, and it will be a negative sign in front. So it looks like this. So you're getting this by applying the chain rule. Chain rule is always valid for state functions. We are already acquainted with that. Now, we are already acquainted with the fact that Cp is defined as del H del T at constant P. We already know this thing in context to the first law of thermodynamics. So if del H del T at constant P is Cp, then del T del H at constant P should be 1 by Cp. So this particular term happens to be 1 by Cp. So we find that this becomes equal to minus 1 by Cp del H del P at constant T. So this is our second equation, equation number 2. In fact, this equation has got a very important physical significance. This equation has got a very important physical significance. From this particular equation, one can determine del H del P at constant T. One can determine del H del P at constant T by the value of mu jet. So this equation helps to determine del H del P at constant T experimentally. How? You see, experimentally we know the value of mu j t. Experimentally we know the value of mu j t. By literature we know the value of Cp. So if these two parameters are known, then obviously del H del P at constant T can be determined. Then obviously del H del P at constant T can be determined. Okay. So this is mu j t. Next. We have got mu j_t to be equal to del T del P at constant enthalpy, and then it turns out to be minus 1 by Cp del H del P at constant T. Now from the second equation of state, one can replace del H del P at constant T by V minus T multiplied by del V del T at constant P. That makes mu j_t to be equal to 1 by Cp whole multiplied by T multiplied by del V del T at constant P minus V. So this is one more important equation. Let us name this equation as equation number 4. Sorry, equation number 3. Okay. Understood. Now, one more equation can be obtained. You see, we already know that alpha is equal to 1 by V del T at constant P. That means del V del T at constant P can be replaced by alpha V. As per definition of coefficient of thermal expansion alpha, we can write alpha equal to 1 by V del T at constant P. So this is replaced by alpha V. Therefore, mu j_t becomes, you see, you can take V common. So it becomes V by Cp whole multiplied by alpha T minus 1. So this is another expression. And this is the fourth expression. So these are the 4 important expressions of mu j_t. So in this lecture, we will end our discussion over here. In the next lecture, we'll be dealing with the expressions and values of mu j_t for various different substances like ideal gas, hydrogen, helium, Van der Waals gas, etc. Okay. And then we'll move on to the experimental interpretations of this particular parameter mu j_t. Okay. So bye bye for now, and we end our lecture over here. Thank you all.